And welcome on the Berlin Users Group meeting. So today we are going to talk about deep learning, and we are going to have a workshop about deep learning. So a word about us. So we run a company that provides data science training, and this training is focused on companies. So it's custom training, custom data science training for companies. And the philosophy is to actually have the training really hands-on, and to make participants learn rather than just sit, listen, and fall asleep. So I hopefully will convince you that it works like this. So the topics that we are covering are really broad. So it's related to machine learning, deep learning, data processing, and introductions to R and Python itself, and many more. So you will have this presentation in a minute on your computers. So there is a website you can visit. So yeah, and we are essentially also data science practitioners. So I work on my daily basis. I work as a data scientist in a company that is called Pearson. I don't know if you know that in Poland, but it's a worldwide company. So we are practitioners ourselves that just want to share our knowledge as well. So, and a couple of rules for today. So we are really just here to learn. So don't hesitate to ask any questions. If I start, saying something stupid, feel free to interrupt me and say if I'm wrong or that you don't understand. So just raise your hand, and we'll figure it out. So if it's a question, then we'll discuss. And if it's a technical problem on your computer, so we have the other Mikołaj, who is your best friend in terms of any technical problems. So feel free to interrupt me and to ask questions as needed. Okay, so a bit on the dataset and the problem that we are going to work on today. So we'll be working on a publicly available dataset containing the features of some Airbnb properties. So is there anyone who don't know what is Airbnb? Raise your hand. Everyone knows. Right, so we have we have data about those properties. So, for example, the number of bedrooms, number of bathrooms, and we are interested also in the price of this property, so price per night. So the problem that we are trying to solve is really a kind of like a toy problem for deep learning, but it will help to really kind of visualize and convince you that deep learning is not that hard, because we'll be trying essentially to predict the price of the property based on its features. So keep this in mind. We'll be like, inputting like all these features like number of bedrooms, number of beds, etc., and we'll be trying to predict the price. Any questions so far? Okay, so the plan for today, so we are going to talk a bit like what is deep learning essentially, and we are going to cover the components of the neural network, and we are going to talk about what is Keras, and we are going to implement a simple neural network that will do the thing that I just described, so predict the property of the price. And about the technical stuff, so this slide deck is available at this link, and I would really ask you now to type this in your browser and open this. So once you have this slide deck, you essentially have everything else. Because the second thing that you can just click if you open the slide deck, but you can as well type from here, is Google Colab Notebook. Who of you have ever used Google Colab? Raise your hand. Some of you. So Google Colab is like Jupyter Notebooks. So if you know that, but it just happens in the cloud, and you can think of this as a Jupyter Notebook on your Google Drive, on your Google account. So I will give you like 30 seconds to get the slide deck. Let me know if it's working. Yeah, I see it works. So that's good. If you opened that notebook, it should be here. There is I have this one as well. You should see something like this. And what I would like you to do is essentially create yourself a copy of this notebook, because this notebook is just read-only. And if you go like File and Save Copy in a Drive, it will create you a copy. And I want all of you to copy that notebook, okay? it should open up in a new tab. Okay, so basically let's get to work, right? We are set up. So first of all, we need to know what is a neural network. And who of you worked with neural networks before? Like some of you. Like, and what is your experience? What have you been doing?
I try to predict the structural condition of a sphere.
Okay, that's interesting. Okay, and have you succeeded, or oh, you cannot say, maybe? Prefer not to say. Okay. Okay. Okay, nice.
I didn't spend too much time on the
yeah. Sure.
So we support for classification and also for semantic segmentation, mostly CNN.
Yeah. Works for you. That's good. So, you know, for some people it worked, for some it didn't. So there could be a lot of cases for this. So this is just a workshop for beginners. So let's start from scratch, because most of you, as I saw, like haven't worked with neural networks before. So what is very important is essentially that neural networks is just a complex function. So what is a function? A function is some kind of like a construct that, given specific input, it gives specific output. So we are inputting, for example, we will be inputting those variables like number of beds, number of bedrooms, and we will be predicting the output, so the price of the apartment. So you can think of it as essentially a complex function. So the structure of a neural network, so you might have seen this before. So as I said, like there is an input right here. So those are the input variables. This could be our number of beds and number of bedrooms. So those are essentially the input variables that we will be putting into this function that I was talking about. So you can think of it as a function, and this is the body of a function. Here the magic happens, so the calculations happens in there, and here we have the output. So we have the price of the apartment. So this is the basics of the basic structure of the neural network. Okay. So the most important thing is essentially that magic that happens in the middle. So this magic is made out of layers. So you can this thing is called a layer, and layer is made out of single neurons. So these guys over here, those are called neurons, and the network can have essentially many layers, more than one, definitely. So what is a neuron, right? So the layer is made out of neurons. What is neuron? Neuron is the smallest element of the neural network, and in the simplest possible scenario that you can get, it's a multivariable linear function. Is there anyone in here that don't know what is a linear function? Okay, that's good. So in the simplest scenario, it's just a linear function. So this might be surprising for you, but it's true. So essentially, this function just takes you know, the weights from the values from the previous layer, and do some. So a computation for a single neuron looks like this. So we have our values. So we have number of beds, for example, for a single observation. So it's 5, and we have, you know, number of bathrooms. It's probably like 1, right? So we have 5 and 1. So those are the values of the variable, and we are multiplying those values by some weights that are in this equation. So we are multiplying some weight by the value of a variable, and we are adding the second component. So we are multiplying the other value by some weights, and we are adding some intercept, some bias, however you call this. So essentially what you see here is a linear function, and it outputs some value. Any questions?
Is the weight random?
At the beginning, it's usually random, yeah. So I will talk about it in a minute. So because, you know, the thing is essentially, the thing that the neural network is doing is it's trying to find the perfect weights, because it's the thing. But so just for now, so what is the number of parameters of this selected blue neuron? Do you have any ideas? 3 is the correct answer. So we have the parameters. So this x1 and x2 is the data we have. So this is not parameters. So we have weight 1, weight 2, and we have some bias to the intercept of the linear function, right? So those are the parameters that, essentially we need to find that out, essentially, for this to work. Okay, so keep in mind this equation, it's a linear function, and keep in mind that this guy had 3 parameters. Is that clear, or? It's good, right. So, and once we calculate this value, then it's used as the input just for the next layer. So we can have more than 2 layers. In this example, it's 2, but it's just stacking, right? So this value is used by those 4 linear functions, and it goes all the way down. So in the simplest possible scenario, I'm kind of putting an emphasis on this because you can get much more complex, and we will get a bit more complex. But in the simplest scenario, such a network is built out of multiple connected linear functions. So yeah, so once I was learning this, I found it a bit surprising that the linear function lies underneath, but that's the basic idea. Okay, so how does it all work? So the goal of the network, so as we've been talking about, is to find those weights for all the parameters. So essentially, once we are training, so we are as close to the original data as possible, right? So this is like a regular prediction problem. So we want to minimize the error, and we want to find some weights that will minimize the error, right? So training the network itself is the process of adjusting those weights, right? Okay, so I've been talking about neural networks, right? But the title of deep learning. So what is deep learning? So we call using complex neural networks with many layers deep learning. So deep learning methods are, in general, as well, still complex functions. So the question to you is, what do you think means many layers? Yes. How many layers is many? When it is deep learning, when we can call it deep learning?
More than one?
Yeah, essentially, most of the sources says that it's more than one, but it's more of like a philosophical question. It's like how many cars standing like in front of the traffic lights creates a traffic jam? Is it like 2? Maybe if the lights are short, 2 is enough. So that's it. So if in general, if we have more than one layer, we can call it deep learning. So, and then why deep learning? Why at all are we bothering with this? So the thing is that once the data volume is very large, it generally outperforms the standard machine learning methods. Like by standard machine learning methods, I mean like, I don't know, random forest and things like this. But the data volume essentially, yeah? The data volume essentially needs to be huge. So it's just like, just to give you a sense. So it's just lines drawn with a pencil. But once the data volume reaches like a certain point, up to the point where, up to some point, so the performance of the deep learning methods and the regular machine learning methods are similar. But once the data volume is really huge, the complex neural networks can essentially find those nuances and figure out, some complex relationships better than the regular machine learning models. So that's the general idea. That of course it's not always. So don't think that it's panacea for everything, for every problem. But it's general thing to keep in mind that if you want to train the neural network from scratch, you need a lot of data. And with a lot of data, I'm saying like millions or billions of observations. So
terms of data points, like sample size,
yeah.
or rather, I have 150 variables.
No, like me.
Potentially could fit, and I need to filter them out.
Yeah. As well, I would say, but if you have like 4 samples and 150 variables, probably no machine learning algorithm can handle this. So just Yeah. So but just one thing to keep in mind also is that so you asked me like, where do I get like 10 billions of data points? So there are some ways. So because this is if you want to train the neural networks from scratch, and there are some methods that you can use a pre-trained network. So somebody have already put like 10 billions of observations, for example, for classifying images. And this network already can recognize the birds, dogs, and cats, for example. And you want to recognize the specific birds. So, for example, I don't know, you want to figure out if that's a sparrow or something else. So you can, and you don't have that like billions of samples, but you have like few thousand of photos of those specific birds. So you can use that pre-trained network, like train it further on your observations to actually serve the purpose. So the question, if you need that 10 billions of data points, is arguable, because you don't always need, because you can sometimes, for some problems, use some pre-trained networks, but it's a bit more complicated. But in general, if you want to have the structure like we saw previously, and we want it to perform well, we need a lot of data. So this is what I wanted to say, essentially. Okay, the applications. So we can essentially use deep learning to solve most of the problems. So what you see over here, maybe you have already seen this before. So those are handwritten digits, and it's a very popular data set in deep learning. So we have images of handwritten digits that we want to classify as 1, 2, 3, 4, 5, 6, 7, 8, or 9, or 0. So it works well for classifications of images and, for example, sound. So for unstructured data, and we could also use it while building like complex autonomous systems. For example, like self-driving cars. It's hyping right now. Also, we can try to apply that to everyday problems. So like classification and regressions on tabular data. So that's what we are going to do today. And this example that we have selected was selected on purpose because it's much easier to understand this on the tabular data, like at least for me, than on images, because you don't need to pre-process those images and do a lot of crazy things just to put them into the neural networks. And if you have a tabular data, you can basically input it to the neural network straight away. So I just want to keep you in mind that the problem we will be trying to solve is more like of a toy problem for today. But yeah, in general, in most cases, it's applied to unstructured data. So just a reminder, what is machine learning, what is deep learning? Those are all like very popular buzzwords, and artificial intelligence in general. So essentially, artificial intelligence is everything that is not stupid and mechanic or electronical. Machine learning is a group of algorithms. And deep learning is essentially just a subgroup of the machine learning algorithm. So it's just another way of predicting and classifying things. So I just want you to remember that essentially deep learning is machine learning. Okay, so how to build neural networks? The answer is that with Keras. So Keras is a high-level library allowing to build neural networks, and the ultimate goal is that it's really easy to use and to allow to build networks really quickly. So if you have like multiple layers, there are a lot of computations that you don't need to take care of by yourself. So Keras will take care of it for you. So the typical process can be divided into a few stages. So first, we need to define the structure of a network. Then we need to define the way that the network is trained. We need to train this, and we need to evaluate if it's working, right? And then we can make predictions. That's the last steps. So before we move on to the first stage, I would like to show you a demo of what be done. So essentially, this will be based on empty cars. So if you are our users, I don't think I need to say what the data set is. So there is a package. There's our package. It's just called Keras that you need to install and load. to actually use Keras, right? If you haven't ever used this notebook, then you execute a cell by pushing Shift and Enter. So then it executes, right? So, right? Shift Enter isn't working. Maybe, yeah. In my Command Enter works as well. So Command Enter, Control Enter, Shift Enter. Maybe, I don't know, something with Enter. Just so and it should work. So coming back. So what I would like to do in here is I've selected a few variables from the empty cars dataset. So you see here that we have the number of cylinders, the disposal weights, and miles per gallon. And let's say that essentially the problem is to predict the economics of the car, so the miles per gallon, right? So how many fuel it's using with those few variables. So with number of cylinders, disposal, and weight. Yeah, it installed. I will load the libraries. I will just select the data. Yeah, and I need to split my variables into the variables that are input variables, so the top of the network that you've seen, and the output variables, so the bottom neuron, right? So I'm splitting my data set. Maybe can you see it from? Is it better, or it should be even larger? Good. So I'm splitting the data set. So the first data set will just contain the columns that will be the input variables, and the second data set will contain just the final variable. And I need to convert it to a matrix type, because that's what Keras needs to have as an input. So I need to start essentially with defining the model structure, so the network structure. So you've seen these neurons on this, the structure of the network. We need to define it somehow. If we want to have 2 layers, 3 layers, how many neurons, etc. So first of all, we need to create something that you can think of like an empty network, and this function is used actually to create an empty network. So you can think of it like an blank piece of paper when there is no layer, no neurons, right? And the function is called Keras model sequential. It will create an empty model for you. And then you execute further functions on this model to build the structure of the network. So the main functions we'll be using is called layer dense. It adds a layer. A very important thing to remember is that a first layer needs to have an argument that is input shape. And the input shape is essentially how many variables are you inputting. So you are not defining this first layer. The first layer is essentially the data you are putting in. So we will be putting 3 variables in here. It's cylinders, disposal, and weight. And units is just the number of neurons. And you don't need to define this first layer, so the input, but you need to define the last layer, so the output. And the output in our case is just 1. We want for each row of the data, so for each car, we want to have a single value predicted, right? We want to have the miles per gallon. So we want to predict one thing, so it's 1 neuron.
What's the first unit?
It's number of neurons. So at my example, there were 4 neurons. Yeah, 1 layer, and here we have 256. We can put 4 in here if you want, but yeah.
For adding new layers, you would have to add a new line.
Yes, if you can just copy this and paste it in here, right? So, is there anyone who does not know what is this guy, like the pipe operator? Okay, so it essentially passes the results of this into this function. So in this context, it works a bit differently. So you can just well, maybe for the sake of this presentation, that's not really that crucial to understand. But it passes the model right here. Okay. So it's the same as you would write it this way without this. So it's a 5 So just to create a pipe and don't need to, reassign all those things. Here, people who are familiar with that operator, take a look that we are not reassigning anything. We are just executing those functions directly on this model. That has some serious implications that essentially, if you want to start from scratch or build a second model or rebuild your model, you need to run that one again because it zeroes your, It 50, so we are going from nothing to a first layer that has 256 nodes and the input shape of 3, meaning that the first layer needs to have that argument input shape defined, because that's and the number of inputs. So that's how it works, right? So
the role that you just deleted, that unit 256 and input shape 3 again. But in that case, the input shape should be 256 because it's taking the...
You don't specify. In general, here, you would go like this. You would go like this, right? You just specify the input shape for the first layer. Okay?
The 256 is still your arbitrary unit.
Yes.
Is it the same of the number of trees and random forest that you find the more computation it needs?
Well, the more complex it gets. So in terms of the empty cars data set, it's definitely a huge overkill. So just
if you just use 500, it's good enough. Others say 1,000. And here, is there any kind of more or less default value that people use?
That's a very good question, very hard one to answer, because this is something like in random forest. It's a kind of like a hyperparameter. So the number of layers itself is a hyperparameter, so that you can try many things on the same data set. The number of units in those layers are, again, hyperparameters of the network. So there are things that might work in one case and won't work in others. So it's like building neural networks, essentially, it's just a matter of trial and error. So I would advise you to start from something simpler, not to stack like 20 layers with like 1,000 neurons at the very beginning of your project, but just to see if increasing really helps, right? So I would go like this path, but it kind of like depends on the problem, the volume of the data you have. So it's essentially hyperparameter. So I arbitrarily choose 256.
A good suggestion to start from 20, let's say, and increasing gradually, or starting from 500 and decreasing gradually?
So let me just execute this one, and we'll look up the model structure, right? So the summary function, if you execute summary function on your model, it shows you the summary of what you have, right, of your structure. So we have like the first layer, and it has 256 units, and we have the output layer, which has just 1 unit. And the total number of parameters that needs to be adjusted is 1,281. So if we have like 20 observations, they are probably not going to be adjusted properly. So it's a matter of between the volume of the data you have and the number of parameters. So anything that sounds possible would probably work. So this function is really useful just to measure the number of the parameters the network will be trying to adjust, right?
So you said in the last layer units equals 1.
Yep.
This makes it a regression problem.
Yes.
Okay? So if you said that you turn into a classification problem or into a regression problem?
Your intuition is very good. Kind of. I will because, for example, for a binary classification problem, you could return a single value that is you can treat as a probability of being it in a given class. So you don't need 2 values. But if for example you are doing a multi-classification problem, then yes, then there will be more values here. So
So
Just a technical question. We did not assign, when you pipe the model through the layers, we did not assign, so it's an implicit assignment?
Yes, so it's essentially, that's a very important thing that I thought I was not clear enough. So yes, so it works like this. So if you want to zero out the model, so start from scratch, you need to redefine it. You need to redefine an empty page. Because if you have this in a separate cell, and you keep adding, for example, now I will add it again, so then I will just stack more and more layers. You see, now I have 4. So, and if I execute it again, I will have 6. And now the structure doesn't make really much sense because, so you need to remember to actually redefine the model if you want to change something, just to really start from scratch, right? All good? Okay, so we have the summary of the model. Let's see if it's, back correct. Okay, and let's get back to the slides for now. So just briefly summarizing, so initializing the model, loading the library, Keras model sequential is the function to initialize it, and then you are using the layer dense functions, remembering about the input shape parameter for the first layer. Okay, but there is a question, like we have a layer dense. What is dense? Do you have any ideas? Yes. So we have like, in between layers, we have connections between each of the neurons. So it means dense because the connections are really dense, the layers are really densely connected. Each neuron is connected from the first layer is connected with each neuron with the second layer, and etc. So that's dense. Thank you. Okay, here is essentially how it looks like on the code. So this part is represented by the layer dense. We have units 4 because we have 1, 2, 3, 4, and we have input dimension 2 because we have 2 input variables, right? That could be a mistake on my slides. So it's essentially, yeah.
The wrapper from the Python library.
I guess it's input shape.
But on the slides that we are following is input shape.
Good. Probably I was correcting those small mistakes yesterday, and probably I'm showing you the wrong version of the slides. But we had 3 in the empty cars data sets, right? But here I just want to, I want you to visualize how this looks in terms of the code, right? So essentially what we have like right now highlighted is represented by that piece. So, and if you have that layer, it's just this one. So we are adding the layer with 4 units, right? And the output layer have a single unit. Correct. Okay, so sorry for this. Okay, and the summary function just to look up the network structure. So now an exercise for you. So execute the code located in this notebook that you've copied, and it will load the data from properties in London. So if you go over here, so I've already installed the packages. I can load this, then load the data. There is one function that we'll be dealing with later. Just execute it all. And there is one quite important thing over here that essentially creates a baseline model. Baseline model is important. And what is a baseline model?
No, you're the expert. Just by intuition, basically you 0, so you have a standard you can compare against?
Yes, so when you have neural networks, many things can go wrong. And it's good to have like a very simple model. For example, in this case, I will just put the average price of all the properties as the prediction and see how bad my model is. So it's essentially not even a model. But if I put the average price everywhere as the prediction, how bad it is. So and if it turns out that your neural network is worse than that, well, essentially something is wrong. So you need to do something about this. So let's execute this one. So when we put the average, we are essentially off in our predictions by around $70 on average, right? Yeah, thank you. So if there is something wrong, you can see that. Just let me know. I think is it good from the back? Yeah, good. Okay, so and once you execute all, I want you to create a network structure that takes two input variables, has one hidden layer of size 256, and returns a single value. And print the network structure and let me know how many parameters does it have. Okay, guys, so how many parameters are there? 1024. Okay, let's go through this. So I will now initialize my model and add the layers. Okay, so I defined like an empty structure, and now I added the first layer, which has 256 neurons, and we'll be inputting two variables for now. And I need to define the output layer, which has just a single neuron, right? And I can see the summary of my model. Right? So we have 1025 parameters. And how did you calculate it 124?
I have like the number you mentioned. So you mentioned that is the correct number.
So but you guys have 25, right? I didn't remember the number. I thought it's correct because I remember that it's just about 1,000. But this is the correct way of doing this. So if you have this, then it's correct, right? Okay. Any questions to this? Yeah.
Because it's not explicit what it means. The output chain none in both cases. Is this relevant or?
Yeah. So it's relevant because it's about how then the calculations will go, and they will go different ways depending on because you will input the data probably not one observation by one observation, but just in kind of like like you will input like 20 observations at once. And so this will represent essentially the number of observations, and it will vary. So it shouldn't bother you. Okay. Yeah. No, like a little bit, no. Okay, there is a lot of things to cover, and we wanted to do this very simple for everyone who wants to start to actually be able to build something up after we finish. So we needed to make some hard choices and to actually skip some of the topics. But okay, so if we have the structure, let's go on. So now we need to define the way the network is trained, and this is a very important step. So to be able to actually train the network, so to adjust all those parameters, so we have now like 1025, right? And you can think of it, they are initialized at random. There are some random values initialized at the very beginning, right? So we need to go through the process of adjusting those parameters to be as good as possible, to make as good predictions as possible. So we need two elements. We need the loss function and the optimizer algorithm. And the loss function essentially calculates the difference between what our network is outputting and the real values, meaning the data. So if we input the data and the price is the real price in that row for this property is 50, and the network for this input returns 100, then we are probably like 50 off, right? So we need to define that loss function. That could be a bit more complex than just the difference. And we need the optimizer that, given the value of the loss function, will update those parameters so that the function, the loss function, the value of the loss function will be minimized. And this is a bit tricky. So one of the most popular optimization algorithms is Adam, and I won't go into much details of how Adam works. We'll just use this. But I need you just to know this, that the optimizer is essentially the way those weights are updated, right? So it's defining the weight. You have a link that you can find the details about more optimizers. So, and I think that one thing is good to mention, maybe because you might be getting a bit lost. So, so training the network itself will be an iterative process. So we'll be going through a lot of iterations. So for example, we will input the data, we'll see what the error is, we'll change the weights, and we'll input the same data again. Hopefully the error is smaller, but it's still an error, right? So based on this new error, we'll try to adjust those weights again and see maybe the error is even smaller, and we will go like this in rounds just to update those weights a lot of times, okay? Okay, and the mean squared error is essentially a very popular loss function for the regression problems. And if you imagine an error, so we predicted 100, but the real value was 50. So the absolute dollars, right? We are off by $50. So we square this. So 50 by 50 is probably like 2,500, right? So, and we do this for all the observations, and then we take the mean of those values. And it's a mean squared error. Is it clear? So why do you think we are using mean squared error rather than just the difference? Correct. To reduce extremes. So it will give us a lot. It will essentially penalize the very outlying errors. So the higher is the error, the higher is the penalty. So maybe I can write it on the board for you to better see this. I don't know if it will be, you will be able to see all of this, but hopefully. So for example, we have a property that the price was 50 and we predicted 100, right? And the other one was 50, but we predicted 150. So here we are like, the difference is 50, and here the difference is 100. So the difference is just twice, so it's twice like this. But if we square those differences, sorry, so it's 100. So if we square those differences, here we have 2,500, and here we have a difference of 100, so we have 10,000. So it means that if we are using mean squared error, now it's not 2 times bigger, but it's 4 times bigger. So we are essentially penalizing this more. Is that clear? Okay. So that's why it's using, because we will always make some error, but we don't want to be, much off for some of the observations. So we want to penalize the model for this. Okay, and as I mentioned, so I saw your confused faces, so I mentioned it a bit earlier. So the training the network is an iterative process. So we initialize weights randomly, and we essentially make all those calculations, and we get some output, right? So we have the data, so we have the input data, those x's, and we have some random weights. We can just multiply, add, do all these computations, and we'll have the result, right? So we calculate it for all the observations, and we then, based on this, calculate the value of the loss function. At the beginning, it will be very high because we initialized weights randomly, right? So at the beginning, the error is high. And after that, the optimizer updates the weights, and the updated weights, and what's very important, the same data allow to calculate the value of the loss function again. Okay? And the steps 2 and 3 are just repeated many times. So how many times do you think they should be repeated?
Proportionally to a number of neurons that we have, I would say.
Okay, not many, proportionate to the number of neurons. Any other ideas? A lot. Okay, there are a lot of different ideas. So, yeah, until it finds the optimum. So, in general, yes. So until it finds the optimum. So usually it works like this: that you make those iterations until your error is not going down. So you're just updating it, not getting any better. So it's just like you can think of it. So you start from random, the error goes smaller, and then it stops, and then probably you don't need to make more iterations because you won't get any better, right? So kind of an intuition. So the reality is sometimes much harder, but let's keep to this for now. Okay, so how to do all of those in Keras? So you need to execute a compile function on our model object and just specify the loss function with the loss argument and the optimizer with the optimizer argument. So there is an additional one over here that is metrics, and you will see in a minute that if you specify this, you can also see, like during the training, the additional metrics. So for example, if the network says that the mean squared error is 50,000, well, but yeah, what does it say? Like, it's not like very human interpretable. So we, for example, can also add the metric which is mean absolute error, that is just the difference, which is really kind of human interpretable, and see how our model performs and what is like the average error of the model. So this is not used like for the training, for the adjusting those weights, but it can be just printed for us to be able to understand how the model performs. Okay, so there are more metrics for more types of problems. You have the links. Okay, and so we define how the model is trained. So now we need to train it. And so to train it, we use a fit function, and we give the data. We give like, you know, the data frame that contains the input variables, and we give it's not a data frame, it's a matrix. So the matrix that contains input variables, matrix that contains output variables, and we specify the number of epochs. And that's really an important argument because it defines the number of iterations through the entire data set. So, in fact, there are a lot of computation on matrices happening underneath. So, the network, we can go like many ways. We can input all the data at once, we can input it by a single observation, or we can input this in something that is called batches, and I won't dig into much details over here, but you will see that. But the epochs is the most important because it's passing through the entire data set once. No matter if you calculate it observation by observation or use so many ways, but essentially through the entire data set. I just want you to remember this one for now. So, and okay, we trained. How can we look this up? Remember, look that we have assigned this, the result of the fit function, to the result object, and then we can use this result object to actually print the result. So it's like, trained on some number of samples, and the loss is 201.6, right? And we can also use this object to plot. If you execute a plot function on the result object, it creates you how the loss function was behaving after each iteration. Any questions? H dot, it's a value for a given epoch. So after we iterated through the entire data set once, the error was 282. After we iterated another time, it was I don't know, 210. After the third time, it went back to 250, and it was going like this up until it reached 201. That is shown on that is shown on the previous slide. So the 201 is just the last step over here.
Why this huge oscillation?
You mean why it's behaving like this and not nicely down?
Basically between 1, 2, and 3 is a huge oscillation. It's like the difference between the second and the 10th is very small.
Yes. So you're correct. So it's just it's just like a toy example of how you can plot this, but you generally expect the model to behave more like this, but it doesn't always happen. So it means that probably you need to adjust quite a few hyperparameters. Here is just the result of running the empty cars demo. So it's trained on 32 samples, so it's behaving a bit strangely because you normally don't do that on 30 samples. But yeah.
In your term, if you define 8 instead of 10, then you would get this, the result, you would get
this one, yeah. And it's even better because if you rerun it, the plot could be different because it initializes the weights randomly each time. So it's not quite deterministic in that sense. So the training itself, right? Any more questions? It's hard.
Because it's not random, right?
Yeah, so I remember that that causes in the real production environment where you are using multiple GPUs and things gets passed from one place to another, it's getting hard to actually set those. So in theory, yes, in practice it's hard. So it's just what you are trying to achieve essentially is to get to a model, to a structure that behaves quite, consistently between runs. So then it means you are probably good because it's called converging. So if the network always converges to some value, then you have probably created a good, well-working structure, right? Okay, and now third time I'm just skipping to this slide. An exercise for you. So now, based on this, define the way the network will be trained, and once you do that, you can use the function that is in the notebook, and it's called split data. That just splits the data set into training, training input variables, training output, test input, and test output. So if you, I might just show it. Yeah, it's over here. So it takes the data as the argument. It takes the vector of x columns that you want to extract from this data set and the y column. And it returns the list with the train data, test data, train label, meaning the output variable, and the test label, meaning the test output variable. So is there anyone who's not familiar why we are splitting the data? Like, feel free to come up. I can. But okay, so we know why we are splitting the data into training and testing, right? So that's good. So please use that function, and then try to train the model on 5 epochs using the training data set. And for now, we have only 2 variables. We've specified in our structure that we want to use 2 variables, right? So let's use latitude and longitude. Just that, yeah. So if you specify it in the function that creates the data set, you can specify those columns like as a vector, names of those columns as a vector, and the proper data set will be returned. Yeah, you can try to measure the training time, but it's not like the essential in that exercise. And
Should I use the same exercise solutions field because I have only one field here for all my coding, the exercise solution. Is that I always use?
It depends, but I will for creating the data, I will create another one up. But for the training and for building the model structure, I will just use one, just to make sure that if you rerun the model, you always reinitialize it as an empty model. Yes.
So you create a copy of the notebook, which was the original notebook you see here. So every time I write the solutions, you will see the solutions in the view node of this notebook. I don't know if it's clear.
So if you click the link on the beginning of the presentation that you've created the copy, then you will see what I'm writing right here. So you don't have edit rights, but you see what I'm changing. So if for some reason you didn't manage to get this, you can just copy it, right? This is fine, right? So it's just, if you ever fall behind, feel free to view this notebook and copy the solutions or ask more questions. Probably there was some reason Okay, so I will give you a few minutes to try to accomplish this. If there are any questions, feel free to ask. Guys, I see that splitting the data causes a lot of confusion, so I'm going to show you this part, not to waste the time. So I will create myself another cell, and I'm going to use that function, split data, that is here. That takes the model, the vector of columns, so there will be latitude. No, not model, sorry. It's a Z-frame, yeah. Longitude. Yeah. And now we have a list. Split, it will be a list of data frames that essentially, let's see, so it's train data, test data. So my train X in this will be the first element of this list. My test X will be the second element of this list. And my train Y will be the third element of this list. And test Y will be the fourth element of this list. Right? So now I have a data frame, train X, test X, train Y, and test Y. So train X contains the features that we are going to input to the network during the training, and train Y contains just the price column. Okay? Okay, connect it in bigger. So one important thing that you need to remember about the data itself in this exercise is that Keras takes matrix as an input. So we would need to convert all those to matrices. And you should be fine with the data. And I will leave you, like, I won't be giving you any more tips about the rest of this exercise. Let's see. So, but who of you managed to train the model to get some results? Okay. So let's go through this. So yeah. Okay. That might be, if it's less than 10, it should be plotting just the points, like it was like that, like in one month ago. If you plotted less than 10 epochs, then it plotted points. If you plotted more than at least 10, it plotted a line. So are the line or points?
Line without points.
Line without points. Yeah, but there's a problem with points. Okay. Let me go through this then. Okay, so we have the data, and we need to define how. Okay, I deleted the summary because I no longer need the summary. So this is the fit, right? So I also need to have the compile function. And I need to have the optimizer here, which is Adam, and loss, that is mean squared error. And matrix, which is okay, so I've added, first I defined how the model is trained, right? So my loss is a mean squared error and my optimizer is Adam, and additionally I want to see what is the the absolute error, meaning it's just the difference between the output and the real values. And I'm going to fit the model on the trained data for 5 epochs. And we'll see, and just print the results. And we'll see how it goes. If there is any typo, then I should be fine. And in terms of the results, what kind of error did you get? Is it better than the baseline, or it's worse than the baseline? 69. Yeah. Yeah, right? So it's expected, so don't worry. Well, we are going to fix it. So what do you think could be the cause? Definitely. So probably just based on latitude and longitude, it would be hard to get the price. They are probably, giving you some information, because probably properties located like more in the center are a bit more expensive, but it's not enough to actually predict the price, right? So yeah, I got this. So you won't get exactly the same results, because as I said, each time you run it, it selects some weights on random, but the results should be similar, right? Okay, and I saw you a couple of people have problems with plotting, and there's probably some problem in the versions of libraries installed. Like you just get an empty plots, and some of you noticed that we might fix it by providing 10 epochs here. Let's just do 10 epochs then, and then the plots should come up. But it was just visualize the training process, right? Essentially, we get the results, so we are good to go. So I leave it, let it train, and get back to the slides. Okay, so are there any questions about this? About this exercise and about this mechanics? Okay, good. Essentially, let's go through this one and make a short break. So this one is pretty simple. So in terms of the data split, so in machine learning, you usually split the data like 80-10 to 10, like 80 for training, 10% for validation, and 10% for testing. So is there anyone who does not know why do we need a validation data set? Raise your hand, I will explain. All machine learning practitioners? No. Oh.
Training and validation, like I don't know the difference.
Okay, yeah, good. Okay, so essentially, you want the test data not to influence the training in any sense, right? Test data should not influence your training, right? But how do you check, for example, if you need to have like 3 layers or 5 layers or 200 neurons or 500 neurons? So to check how it works, you are using a validation data set. So you are training on training, validating on a validation data set, but then this validation set essentially implicates your choice. So it implicates the training. So it influences what do you choose, what hyperparameters do you choose. So the validation data set is used to test the different sets of parameters, and you select the best set of hyperparameters on this validation data set, and once you have it, you still have this test data set that you can, at the very end, verify the model performance, never touch the training, any aspect of the training. Because, like setting hyperparameters essentially is affecting the training, right? And you don't want the test data to affect the training. And that's why you need the validation data set. Is that clear? Okay. Yeah, but well, yeah. So it's a matter of how you are approaching things, but it usually works like this. Yeah. So it's a kind of like a double checking, not to make any. Okay. So we are also splitting the data set in a similar fashion in neural networks. So we need the validation data set. But if you have a really huge number of observations, so you don't need to have like 10% for validation, 10% for testing. You can, for example, have 1%. If you have like hundreds of billions of observations, maybe let's use a bit more for training and a bit less for validation and testing, because this a bit less will still be like hundreds of thousands of observations. So yeah.
Here, as I read the function here, we are training and testing 9 to 10%.
Yeah.
Right?
Yeah.
You're now in
because this data set has a couple of thousands of observations, right? So it's not that large. We won't be able to. Usually, if you train like a neural network on a really huge data set, it takes definitely more time than we have today. So it could take like weeks even. Yeah. Like if you have like, depending on the hardware you have and depending on the problem you're trying to solve. But yeah, definitely hours.
What would you suggest to shift the computation to GPU instead of CPU to train?
If you are waiting too long, then I would advise it.
Which amount of data more or less is the threshold?
I think, yeah, the amount of data is one thing, but the other thing is complexity of the network structure. Because, the number of hyperparameters increases like, very rapidly once you add layers. So it's also about number of hyperparameters. So essentially, if, for example, on the CPU it trains for an hour, and you can buy a machine on AWS that costs like, I don't know, 50 cents per hour or 60 cents per hour, and you can shorten that time to 5 or 10 minutes, I would advise you to do that. So it will really, make you experiment much faster. So it's more like,
I was asking just because I'm not particularly used to work on GPU, but I know technically and conceptually that if you do less of what the GPU is made for, you are actually delaying your.
You could because the information gets passed from CPU to GPU, but it's on real problems, real data. So you don't need like billions of observations for this to speed up. I think if you have like couple hundred thousands, then you are good to go. Or even you could have like few thousand, but those are images, so those are really big, like so that depends. So if it's taking too long for you, I would advise to switch to GPU. So this is a rule of thumb. Yeah. Okay. Okay, so we've created, someone noticed that we've created, validation data set, but the function created a training set and a test set. So how to create a validation data set? So actually there is an argument in the fit function that will do it for you. So it will actually split the training data you're giving into training and validation. So we set the test set aside, and then now when training, it will automatically split 20% of the training for validation, right? So it's quite straightforward. So you just add the validation split argument to the fit function. So I let you do this. We can do this together. I think it's not. Yeah, so you just add like a validation. It's like, let's set it to 10% over here, like as it is in the exercise. And then when you retrain it, it should also in the results show you both the results in training and on validation.
How to add the testing? Would be the test split also 1%?
No, so testing is not part of the training, and here we are training. So we are now just left the test set aside, and we will take care of this once we have the promising architecture. You are using the test data set only at the very end, so not when experimenting. Just once you're, yes, that's why the validation exists, to act as a test set, like in your ongoing experiments. Yeah, so now you can see that we have some more information. So, for example, we have the values of our loss functions, which are used during the training but are not really human readable. But we also have on the training data set and on the validation data set, and we have the absolute error and the validation absolute error and the training absolute error. So those values might be a bit strange for now because we are using just two variables, but the plot should also work right now. Yeah, they are working, right? So yeah, so well, it's kind of like in terms of the value of a loss function, it's kind of decreasing, but like very, very, like almost not decreasing. So yeah, so it looks like this. Are there any questions to this? Yeah?
The price and other variables are really too
They are. It does. It does. And so it helps to normalize or standardize the variables. And so another problem is that they are on a different scales, which also causes this network to behave strangely. We will get to this point. For now, I encourage you to take a short break. So, and congratulations, you trained your first neural network, right? So probably, maybe your first in your life. So it's trained. Maybe it's not perfect and it's not working that well, but you managed to train this. So let's take 20 minutes break and let's get back at 20 past 12. Okay, so someone chose at some point that probably the results are poor because there is like not enough variables. So let's try to add all of the continuous variables and train the model again and see how the results look like. So what do we need to do to add the variables? We need to modify the execution of the function that is doing the train test split. Right? So, and then we'll have more variables. And what else do we need to do? Yes, exactly. So that's also very important because our input shape changes. Now we are going to have 6 variables. We had 2. Now we're going to have 6. Yes. So preprocessing is I will talk about it in a minute. Yeah. So let's just now see how it looks like. I will do it myself. So I need to go back to the place where my split data function is executed and change the latitude, longitude to all those variables that are on the slide, right? Yeah. So we have latitude, longitude, number of reviews for an apartment, accommodates so how many people can sleep there, number of beds, and the rating for an apartment. Okay, so let's just re-execute this. And here I have an input shape of 2, which I need to change to 6 for this to work right now. Yep.
Instead of listing all the variables, can we call a column name? Can take that as an argument?
Not really, because this is a function that I've just written, like, for this to work like this. So it's not any built-in function. So it's just you want to define. You just can't pass just plain variable names. You need to have the vector of strings. So if that was the question, yeah. Sure. Yes, you can. There are more columns in the data set that we are not going to use, like in this one. So, yeah. I mean, you don't have to type them, like they are here. I just copied. So I copied them from the slide. So I put it on the slide on purpose, like in that format, so you can just take them and copy them. So it should be quite easy. Okay, let's run the model, see if it works, and see the results. So, have anyone got any results? Not yet? Anyone? And what do you have that you think that you did something wrong? So it's like this. Yes, and why do you think it is like this? Missing data. That's correct. So it is expected to have nans right now, right there. Okay, so missing data. in general, neural network cannot accept missing data because of the computations going underneath. And so we changed the columns that we are inputting, and some of them contains missing data. So what can we do about this? So there are many ways you can go, of course. You can exclude those observations. Oh, well, not really recommended. You can apply some data imputation methods. So in the very simplest case, you can just replace it with the average of the complete observations. So the data imputation is probably another topic for another one-day workshop, so I won't dig into much details over here. But so you need to do something about those values. This is important. So the next thing is to actually inspect the data and get rid of missing values where needed, and train the model again and see how it performs. So what do you think? I would think that just place the average there for now, okay? And now, a couple of minutes for you. Okay, so how can you check which columns have missing values? Yeah, I think one of the easiest way is to actually use the summary function. So I will create another cell right here. So I will just write the summary of my data frame. And yeah, I have a summary, so I have a lot of statistics, but for example, here I see that beds column contain 132 NAs, so somehow didn't give us information about the number of beds. And the review scores rating also have NAs. So those are the only two columns in the data set. So let's replace that with mean. I won't dig into details if that's the right choice and option from the perspective of training any machine learning algorithm. Let's do this right now, just to allow the network to train. Okay, so what I will need here is essentially then mean of number of beds for but I need this for the complete observations, right? And I also need the mean of review scores rating. Right, okay, so I have those means. I can print them so we can see what they are, if they are not some stupid values. Hopefully not. No, like mean bets 174. Probably there are no floats in this column, so we might come up with something else like 2, for example, because I don't think that any host put 1.74 bed in his listing. But yeah, but we can put this value and this will work fine. So just for the sake of this workshop, probably you would need to fine tune it if you were like doing some real job, right? So how can you replace NAs? Yes. So there is a function. Let's call it like filter it PDF and do to replace an A. It's a function from tidyr or dplyr, generally from the tidyr stack, and it takes a list as an argument. So it's a list of columns. So it means that please replace me all missing beds with mean beds, and replace review scores rating with the mean of review scores rating. Right? Let's see. And then if we do the summary of this filtered data frame right now, we should see no missing values. And that's correct. Nothing shows up in here. Previously we had this here, now we don't. So we should be good to go. We just need to replace this original data frame in the execution of our split data function, because now we want to split the data that is essentially that has those NAs replaced, right? Okay. And if we run all those, we should get our results back again. Let's see. Has anyone succeeded and it worked? Or raise your hand if you did. Like yeah. Okay, good. Okay, so we have this right now. So what does it say? Like we don't have an ace, and we can see, for example, that essentially the absolute error, so the human readable error on the 60.68. And do you remember what the baseline was? The baseline was 69. So we've beaten the baseline, although very simple, but we did, so that's a success. We definitely beaten the baseline, so we have the model that works better than just inputting the average, right? I'll give you a second just to think about this, replicate this, and ask any questions. Okay, I think we can continue. If you still need this, remember that you can view this notebook and you see what I'm writing right here. If you click the link from the beginning of the slide deck. If you don't see, refresh the page and it should be okay. Okay. So at the beginning I was talking that that we are like in the simplest scenario, it's a linear function, that neuron is a linear function. But if we connect a lot of linear functions together, essentially what we get, it's kind of like a linear relationship, right? We're still like searching for a linear relationship between variables, which is not the case in most of the scenarios. So by default, it's made out of linear functions. And linear dependencies are not what we are looking for. So how to make this nonlinear? Any ideas? Yes, so you whether knew something about neural networks before or looked slides forward, but yes, so we can use a function that is called the activation function, that essentially allow us to add the transformation of the linear function. So if you remember the equation from the beginning of the workshop, we had only this, right? We had the linear function. But maybe let's apply some other function to the result, to the value of this linear function, and if that function here is not linear, then we are essentially the relationship not linear, right? So, and all the other stuff works the same. So calculated value is used by the neurons in the following layers, right? So that's basically it. So what kind of activation functions we have? So linear function is a kind of an activation function, right? Because if we imagine that if we haven't applied anything, we are actually using a linear activation function. That means that if our neuron returns 4, we are essentially returning 4, right? Because that's the value of the linear function, and that's the transformation. So there's no transformation. This is like the identity, right? No transformation. If it outputs 0, it's 0. If it outputs 4, it's 4, etc. This is the linear function, and this is the linear function like after applying the activation. But we can use some other function. So for example, this is the sigmoid function, and its values ranges from 0 to 1. So for example, if your linear function returns 0, it will make it 0.5. But if it returns 6, it will make it almost 1. Okay, so we are applying like this kind of like non-linear function to the activations, and there are more. There is, for example, a hyperbolic tangent, and the ranges outputted ranges from -1 to 1. That range is kind of important, especially when used on the output layer, but that one in a minute. And this one is really interesting. It's called ReLU, and it's one of the most popular, actually. And it looks linear, but it's not, right? It's an elbow. So an elbow is not linear. It's kind of linear. So everything that is, if we return anything from the linear function that is below 0, it becomes 0. And a part of this, it's a linear function. Right? So it looks kind of linear, but it's not linear. So, and it's very, very popular. And I would say that you are asking again which one to use, and I would say that you need to try. So you might want to try this one first. So there are a couple of problems that you can read about here with using sigmoid and hyperbolic tangent. So I won't dig into much details right now, but this one seems to solve them. Okay, so which activations to choose? Actually, in case of those layers right here, essentially this function works on each neuron separately, and so ReLU is a popular choice, right? So for the blue ones, just use ReLU, start from ReLU. You can use sigmoid, you can use hyperbolic tangents. There are more, essentially, so you can read about it in the internet. But you can essentially use anything you want, and with a trial and error, see how it behaves. But the special case is the output layer, which essentially, where this function depends on the type of problems we are trying to solve, right? So if we are trying to solve a classification problem, like binary classification problem, so we are trying to output something that can be interpreted as a probability of something being, being in a class. So for example, we are trying to distinguish cats and dogs, and we are trying to return the probability of something being a cat. So this could not go like from -1 to 1, because what does it say then? So it's good then to select a function which matches with what we actually want to output. So in case of a regression problem, well, a linear output function probably works well, because we want to have the values like from from -100 to 100, right? Maybe for the property prices, ReLU is a good choice, because you can have negative prices. So it depends on the type of problems, actually, that type of problem that you are trying to solve. So you need to be really aware of, here you can put anything and it works, and here it won't. So you need to be careful, especially in this part. Okay, so as I said, like it's when it's a binary classification problem, a sigmoid is a preferred one, because the predicted value are in range from 0 to 1. As I said, like multi-class classification, there is a softmax function. I won't dig into details right now how it works. For regression, it could be in most cases linear, and that would work. Okay, so now a quick quiz. So which activation function to choose on the output layer when detecting spam emails? Okay. Tang, no, because it's from -1 to 1, so it won't work that well. Yeah. So sigmoid works, right? And predicting air temperature? Linear. Yeah, because it's like the range is very, very broad, right? And classifications of dogs, cats, and birds in images? Yeah, so it's a multi-classification problem, so it's a categorical cross-entropy works. Okay, so we know the theory, so how to do this in Keras? So we can essentially do it using the activation layer that happens after our dense layer, right? So we have activation ReLU, right? Activation sigmoid, etc. So, but it's a bit of, a lot of writing. You can just give that argument here, which says what activation belongs to this this particular layer. So, for example, here we have activations ReLU on the first layer, and on the last layer we have sigmoid, right? Any questions? Okay, if there are no questions, then there is an exercise. So this exercise is made out of two parts. So first thing is to add 2 additional dense layers of size 128 and 32 to the existing infrastructure. And I mean the hidden layers, right? So they will need to go like in the middle, right? Yes. And add proper activation functions that you think suits each layer. And train the model again and see if there are any differences. Okay, so guys, I think, so who managed to get some results? Are the results better or almost the same? Someone got something a bit better? A bit better, yeah. I think they should. 0.7 there. Yeah, so you won't get like astonishingly better results just by setting this stuff. So if it's a bit better, then probably it's right. So let's add more layers. So as in the exercise, so one should be of size 128. Just to remind, if that's another layer, there is no input shape parameter needed. Yes, so I'm now, so 2 layers, add proper activation functions. So we'll go over here. So what functions have you set? Okay. You can set ReLU everywhere. Yeah. And it should work fine, right? And why not? And why not?
Because that should be just the output. So why that activation doesn't work anywhere else?
And can the price be negative?
No.
So why do you want to allow the prices to be negative? So
wasn't worse because I don't want to change the inputs. That was my fault.
but that's not this is a regular layer. The input parameter is just that that we are going to input the. So it's the same layer as this one. So it's just the first one needs to have the input shape defined.
Yeah, I know. I just thought that if you add the activation, this first,
yeah,
and say as ReLU, it would take as the inputs. All that are negative would transform into 0. It doesn't happen.
No. It takes the input, it does, so it takes the data. The data, each data point, each variable is multiplied by some weight. And it creates some result, and this result of the function is then put into the ReLU function. So if the result of all the computations is negative, then it's resulting 0, right? And coming back to why we can put ReLU here, is because we don't want our prices to become negative. So it will essentially increase our error. If at any point the algorithm decides that the prices, return minus $100. So the error for this observation will be huge because it's impossible, right? So we can, but we don't have to. Like linear works fine as well. But it's just to remind you that we can do that, yeah? So you are saying that just without this is better. Okay, so let's leave like this. It's just a matter of, so we are experimenting. So I think this should work, but maybe, so if you suggest this, let's leave this. So it makes sense as well, right? So, and if we're going to get, so how do we set the number of neurons in each layer? That's the hard part. there is no recipe that actually will guide you through how this should look like. But what I can recommend is start from something small. So start from a neural network that has like 32 neurons in the first layer and 8 neurons in the second layer, and that's it. Start from like 2 layers and like start them small and see if it gives you some results, and then see if actually increasing the number of neurons, which means increasing the complexity of the calculations like underneath, gives you some better results. Because if not, then it doesn't make much sense to do that, right? Because it will just run forever and train forever. Okay. So let's leave like this. So if you say that's the best way to go, let's do this. So how better did we get? Like 0.7, right? So something like this, or?
We know there is a 0.3.
Excuse me?
Without that activation in the last
yeah.
layer, 0.3.
Okay.
Absolute error.
Okay. .3. We'll see. Okay. So I think I get a lot better on the validation data set, because I had like 59 over here last time, and I have 52. So depending on what are you looking at, so which value were you talking about? Okay. Yeah. But that could be a bit lower. But essentially, anyways, we improved, right? This one is calculated on a training data set, and this one is calculated on our validation data set. Yeah. So I would encourage you to look at both. They should both be down. So
one is 90% of the training data, and the other is 10%
yes.
of the training data.
Yes. Yeah, so it might be, yeah, so of course, so this might be related to how the validation data is chosen. So that's, you need to choose the data sets carefully. So we might have introduced some bias in while splitting, because we've just split the data set randomly, right? So
the validation may be much more sensitive to noise, or
yes. Or for example, if the validation contains like only a single district of Berlin, and the rest is like other districts, for example, so it's like it could be many cases, right? So you need to be careful, but that's a separate topic, how to split the data correctly, right? So yeah. So any questions to this? Okay, so we're coming back to the data preparation, because there were questions about this at some point. So essentially, so the deep neural networks can figure out the dependencies on its own. So we don't need to do some feature engineering, like, I don't know, some multiplication of variables. Sometimes we do that, and neural networks can figure out it by itself. But the proper data preparation can make the network train significantly faster and essentially even converge at all. So reach the minimum error that is essentially possible. So what we can do with the data is actually data normalization. So we have a variable, like I think it's longitude, on a scale from 51.3 to 51.7. And we can make it on a scale from -4 to 4, right? So that all the variables are on a common scale. So that one is important. It helps the neural network to converge faster. So that is an important step, right? So you can do a couple of things, so right here you have something that is called standardization, as far as I pronounce this correctly. And so it would put our variable on a scale of the number of standard deviations from the mean, on the left or right. So that's the case not this direction. That's the case here, right? So the mean was set to 0, and we have like standard deviations left and right. So it's centered around the mean. And the second way we can do this, we can essentially get the values in a certain range. So for example, we can go from 0 to 1, and that will also help, right? It doesn't actually matter much in like which way you go. The only thing is that go the same direction with all the variables and do this at all, and this will definitely help. And that's the most important, I guess, sentence, is that if you don't do this, the training could fail, meaning that it can try to learn the dependencies between the variables and adjust those weights, but could not find the proper and the best weights in your algorithm. So that might be a bit like, fuzzy right now, but it just works like that. So usually if a variable is normally distributed, so like the longitude, we could standardize the variable. Otherwise we should normalize, so place it on a scale, right? Okay, so but how to code this in R? This is an important thing. We can use a Keras package. I think that some of you who dealt with machine learning already knows that. Who knows Keras? Okay, a couple of people. There is a function called preprocess that actually transforms the data set with a given method that you can just give to the function. So there is one really important thing right now, is that we need to preprocess, like the preprocess actually creates a way to transform a data. And this way is created based on a training data set. And the same way needs to be applied on the training data set and on the testing data set. And why do we create this way based on the training and not the entire data set? So we are trying to find a way to preprocess the data set. So for example, to standardize. And so we need to make some calculations that we are going to apply, because for example, if you take the training data set, the mean of number of bets will be different than if you have taken the entire data set. And the mean is used to standardize, right? So yeah? Yes, that's correct. So the test data essentially imitates something that will happen in the future, that at the moment of training doesn't exist. So for example, if you have the data coming to be predicted in a month, you don't have the data to calculate the mean right now because it doesn't exist. So that's why we need to do this on the training data set. And this is really important to remember. So this preprocess function creates some kind of a scalar, so this way to transform this, and it's based on the training data set, and then we can apply the same way to the training data set and to the test data set separately, right? Is that clear? Okay. And if you just wanted to have a range from 0 to 1, you just change the parameters of the preprocess function. So by default, it does center scale, which is standardization, so it will center around 0 and make standard deviations. So yeah. Yeah? That's a very good question. I think you need to, it depends on what do you do with DNAs. So I think that after, because if you inputted, for example, reduced cause rating of 92, as far as I remember, so this needs to be scaled, right? We can't leave 92. Or then we would apply a different, then we would apply a different value, so it might work as well. So yeah. I think that it would be better. Yeah. So to scale it before we input missing values. Is that your like sense? Yeah, it makes more sense. Yeah.
How will the thread process handle the missing data? You just remove?
I would need to dig into that, how this particular function handles the missing data. Maybe it removes, I don't remember. You would need to dig into the documentation. Maybe it deals with the missing data itself. Yeah, I would need to check this, but or maybe some of you know. Okay. Anyways, let's try to do something with this. So let's try to apply some transformations to the data set to make the training better. And train again. And see if it helps. Who of you managed to pre-process the data and train again? And have you pre-processed before removing the missing value? After. Okay. That's good. Yeah. So what you will notice is that, like, at some point, probably in most of the problems, the network will reach the same performance, but you will need to train for a larger number of epochs, because it will take the network, like, intuitively a lot more time to figure out that the variables are on different scale. So the weights are initialized like with this very similar values, right? At the very beginning. So if we multiply this weight, for example, the weight is initialized to 0.1. And if you multiply 0.1 by something on a scale from 0 to 1, you will get some fraction. And if you multiply it by 1,000, you will get a very high value. So the process of adjusting will be longer, and sometimes it could fail. So that's also the case. But in some cases, you will get the same performance, but just you would need to train. So that's how it works. Okay, so I will just try to apply this as well. Yeah? I mean, probably they are. So that's the problem of local optimum is, yeah. So yeah. 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 Why not? So what we did, we hadn't any missing. We didn't have missing values in the price itself, and in the baseline we are just comparing the prices for each. So we've averaged the price. So doing the baseline, we didn't need to do with the missing values. So okay. So then I can pre-process my data. So after the split, I'm going to actually use the preprocess function, put my training data set, center, scale, and then apply it to the train data set and the test data set. And I have new variable names for the training and test sets right here. So I need to actually, in the fit function, say that now I want to train on train X scale, right? So some of you might miss that, so you might train again on the data set that is not scaled. Okay, so let's scale it. And let's retrain and see. So it got better, right? Yeah. No. And have you changed the fit function to use the scale data? Yes. Okay. Yeah. So,
better to transform or either de-transform the when you compare the training with the test, like the way we are running on the test data.
yeah.
That would be the discrepancy using the transformation.
Yeah, so you need to apply the same transformation to the test data set, and that's what we did. But we need to or what?
Or the reverse function. So, for instance, we transform logarithmically.
Okay.
The exponential and
yeah.
on the test data. What do you suggest? To transform the test or to apply the opposite?
No, it's just usually you transform the test data, but you transform the test data just based on the, like you do it the same way you transform the training, right? So it's the most important. So, you know, you don't like create a new way of transforming based on the test set, right? Okay, and so I think that's trained, and well, I got some better results, definitely. So in 10 epochs, my results are better. Now my mean absolute error is 51, and on the validation it's 47. So it's quite better than the baseline. The baseline was 69. So it's still probably, you know, it's not a great model. Don't think that we did something extraordinary here. Definitely not. So if you're trying to predict the price of a property and your average mistake is almost $50, you are probably not yet good to productionalize this, but yeah. Yeah, so some are in thousand, yeah.
You had effort of 4.
Here? But let me just stop right here. Okay, so we are training based on a loss function, right? So the loss function is mean squared error. So this is mean squared error. So this human unreadable, but we are training. So see what's happening. So this is the training data set. So it goes down, right? Quite smoothly, it goes down. That's nice, right? So this is what actually the model is using, this mean squared error on the training data set to train further. So that's why it's going down. On the validation data set, it's not really, because, you know, our validation data set was some arbitrary choice that we made, and that probably, you know, it's a bit fuzzy from time to time. So we are not doing that good job on the validation data set. And if you go down, so here you're talking about that they oscillate, right? So this metric is just calculated, but it's not used anywhere. Like, it's not your target. So your target is a mean squared error. And this one is different, because it's a mean error. And for example, if you predict a property, like a very expensive property that costed $2,000, and you predicted $4,000, so, you know, that might cause like these things here, right? I don't know if it makes sense. So, are there any questions to this? Yeah, go. You mean that this one is flat, right? Yeah. Probably. So there is also one particular thing that no one had asked it yet, but probably someone will. Why do we have an error of 45,000 on the training and 12,000 on validation? Like, it's like huge discrepancy between one and the other, right? It depends on how this is calculated. And for the validation, let me do it like, the answer is that for one of them, it's the average of the metric for all batches, and for the other, it's just at the end of the epoch. So it's using batches, so it's not inputting the data all at once. And this is the discrepancy, this is where the discrepancy comes from. But I would expect that line ideally should always look, should as well look like this. So it's not, so we might be overfitting, which is another thing that we haven't discussed, but it's a generally, if you want to do neural networks, please Google overfitting. And see how you can, what you can do about this. Okay? Okay, so we have quite promising results. You can try training on a larger number of epochs and see if that improves the results. Maybe it will get even better. It takes time, so maybe let's not do this right now. So we are coming to the one of the last phases. It's evaluation, right? So we are very happy with the model. We did our best that we could, and we can't get any better, right? So now there's a time for evaluation. So how our model will perform on the test set, right? So how to do this? Using the evaluate function from Keras. So you put the model and you use the evaluate function where you put your test data and your test labels, and it prints you all the metrics. Right? And how to make predictions? So to make predictions, you can use the predict function, which is, it works like it's very straightforward. You do model predict, and you put the data set for which you want the data points to be predicted. Okay, so now it's time to verify our model in test data and see how different are the metrics on the test set compared to the validation data set, right? Okay, so what are your results on the test set? So my colleague is distributing the surveys. I will be very grateful if you fill this up. Sorry for this to be on paper and not electronical, being not eco-friendly, but if I provided you the link now, you wouldn't fill this up. So that's that's the point. So did you get similar performance on the test set, or a little bit worse? Okay, but in general, kind of like oscillating around the same values. Well, yeah, so that's good. So we've evaluated, and then we are good to go. I need to do this as well. So we have test X scaled and test Y, and this should work. In my case, it's similar. I have the mean absolute error of 49.37. So it's around what I've been getting. Well, good.
What's the value for without normalization?
I think I had 47. 47? Here, this one?
So your mean absolute error drops, right?
I mean, increased on the test set.
Yeah, it's less than
Then on the test set, yeah.
that makes sense.
It does. Like, and then on the test set, not really. So,
My expectation was really high on test set.
Higher, you mean the error will be lower?
No. Higher.
Error was higher. Like error here is error down is, but you mean comparing the training or the validation?
There's increase in the validation from the validation, but decrease from the
Yeah, I guess it's the cause of the data split. So I would expect it to be higher here than lower. Yeah, but this, yeah, it makes sense. It makes, I think. You mean it should be higher than 51?
on the test I got
Yeah.
higher value both of, I got validation, absolute error 56, training, absolute error 58, test, absolute error 60.
That's expected probably, yeah. So, but it's quite high. You should be getting somewhere around 50. So maybe you have maybe you do something differently. But this would be expected.
I compare your script with mine and
okay. Okay. Yeah.
That's the same. I got 50. Then I use this to predict.
Yeah.
And the mean of my prediction is $85.
Yeah, but that's the average price of the predicted property.
The mean of the...
No, it's a mean error.
But we calculate just the mean of the property.
So the error was 69. But yeah, but yeah, I did.
Yeah, quite right.
Yeah. Okay. Okay, guys. So few more thoughts. I think we made it, but just a couple of tips you've been asking around. So just summarizing. So the process of building a neural network is a series of experiments, and there is no like ready recipe that will work on every data set. So you would need to try it on your own and see if it works for you. So you can experiment with number of layers, with neurons, with number of epochs, with the batch size, with activation functions, optimization algorithms, loss functions, and many more. And it's very important just to remember just to use the proper activation function for the output layer. This is a problem that is really often when you begin. That is happening quite often. So we've learned what is neural network. Sure. So we've learned what is a neural network and deep learning. Based on the Keras R library, we've built a model that is working, so it's predicting the prices better than the baseline, so that's good. However, like it's good to remember what I've been saying at the very beginning, that this is just a toy problem, and the benefits of deep learning usually happens when data set is much larger and much more complex than just a few columns and a few property prices, right? So just remember that. And I hope we actually convinced you that those deep learning techniques are not that hard, right? So it might be overwhelming. For me, it was when I was learning it back like years ago. But I think that if you dig deeper what's inside, it's not really that hard. So I really encourage you to keep experimenting and keep learning. This is a real fun. And so summarizing, if you also need a data science training, so we are doing data science training. So if you want one, feel free to contact us. Those are our email addresses. Feel free to shoot an email and we can set this up. Thank you.